you. All right. It is December 4th. It is December 4th, ladies and gentlemen. Today is the last day. No. Miss, where have you been? My daughter's been sick. I heard. No, I asked. So, we have today's work, which notes is a little involved today, but it is the last day, so that's
yes.
And then you'll notice that I've written on the board, we have review day on Thursday and Friday, and then a test on Monday. That's the test for chapter 30.
This Monday?
After that, we'll do a couple of easy worksheets that just review basically the Pythagorean theorem, so it'll be a couple easy days. I'll also start on Tuesday, the 10th, I will put up the review for the final exam. Officially, our review days for the final exam will be Thursday, Friday, and Monday, and Tuesday. And then your final exam is on Wednesday. And this is very exciting. It's very exciting for me. I'm very excited and I'm teaching my keep that in mind, but you can obviously, the couple of worksheets we're going to do are relevant. They pertain to trigonometry for us, so it's a good review. For that's coming up in January. Yes, there will be a review for the final exam that is extra credit. So it's a review for the final exam. It's also extra credit. It's worth 10% of your final exam.
Oh, bet that, John.
And how is that? You got test tape.
He has test to take in a lot of classes.
You got it. Do you want to do it now? Yeah. Are you, I would like to give it back. Like I can't pass them back yet. Okay. Let me know when you're ready. All right. Okay.
It's a Wednesday. You study tonight and take your
You want to do that? Okay. All right. So here we go. Last day of notes. These are, this first one is a challenging problem.
I know you've heard it.
It is out of your book. I assigned it the first year I taught pre-cal, and it was just not so awesome because it's hard. This is definitely a hard one. On the scale of problems I would give you, this is not in the realm of possibility. It's hard. Example 1. The ones out of the book are a bit easier. Yeah. So the number of bacteria in the culture is increasing according to the law of exponential growth. After 3 hours, there are 100 bacteria. And after 5 hours, there are 400 bacteria. How many bacteria will there be after 6 hours? So most of the problems that I'm giving you today break themselves apart into do this first, then do this, and then do this. It's a 3-part process. We're going to do that here as well, but it's all sort of in one paragraph, which makes it a little bit harder. Plus the problem itself is just harder. But so we're starting out really hard. The others aren't quite so bad. Okay. So first, the number of bacteria is growing according to the law of exponential growth. Well, the law of exponential growth is basically the PERT formula. A equals P times e to the RT, okay? We use this model with a base of e because e is, what is e? A number. What is e?
Less than 2 the number.
Not quite 3, not quite 3. 2.7182. Yeah, what is e? Not quite 3. Okay. But E is a naturally occurring number. It's a natural growth factor for a lot of things, okay? And so we use this all the time. Now, your book actually uses the model Q equals Q naught times e to the KT. Are these different or are they the same?
The same.
They're exactly the same. And they use Q to represent a quantity. Q naught, Q sub 0, is really just the initial quantity that we have, or the initial quantity of bacteria. And then you know, that's the same as our P. For us, the P stands for principal, but the idea is the same. It's the initial quantity, the initial amount that we're starting with. So it really doesn't matter what letter we use. The R is our rate, our growth rate, and so is the K. It's the rate that something is growing or decaying at. Whatever letter you use, it doesn't matter. And what is really important is the A and the Q here. The A is the amount after T hours or months or days or weeks or whatever your unit is. And here, the Q also represents the quantity or the amount after T hours or weeks. So after a certain number of hours have passed, then we have this amount of bacteria. Okay. Whatever model you use or whatever model your book uses, it doesn't matter. So we're going to go with what we're comfortable with because we already have this memorized, hopefully. And so I'm just going to use PERT because I like it. Then I've got some information. After 3 hours, we have 100 bacteria. So, well, that's an ordered pair. There's 100 bacteria. And after 5 hours, there are 400 bacteria. 5 hours, there are 400 bacteria. And, well, if I know that, then this is exactly what we did on Monday, where I said, hey, here's these curves. What's the equation that passes through these 2 points? This is exactly the same thing, okay? So we're going to plug in what we know. This 3 represents time. After 3 hours, there are 100 bacteria. I can plug that in for the A and the T. So I have 100 bacteria equals P times E to the R times 3. They didn't necessarily give me the initial bacteria, the P. I don't know that. I only know how many bacteria there were after a few hours. So I don't know how many there were when time was 0. So we have to figure that out. So I'm going to do just like we did before, and I basically want to isolate the P. And it's going to be a substitution problem just like we've done before. So I'm going to divide by e to the 3r. So e to the 3r cancels out, and I get something for P. It's kind of crazy. 100 over e to the 3r. Now I can take this 100 over e to the 3r, and I get to put it in place of P in my equation here. So 100 over e to the 3r times e to the RT. So I basically just plugged that right back in place of P and rewrote my model. And now I get to plug in my second ordered pair. So I'm going to plug in my 5 for the T and another 400 for A. Times e to the r times 5, or 5r. Can I clean this up at all?
Yes.
Yes. What cleans up here? The things with e, yeah. E to the 5r over e to the 3r is e to the 2r. Top minus bottom. They have the same base. We get to subtract those exponents. So I have 400 equals 100 times e to the 2r. Now how do we solve for r? Divide by 100. That's easy. What's 400 divided by 100? 4 equals e to the 2r. And then how do we solve? Natural log of both sides. That allows my power to drop down. So the natural log of 4 equals 2 times r times the natural log of e. What is the natural log of e? 1. And then how do you get r by itself? Divide by 2. Divide by 2. So r is approximately, let's see, I can plug that into my calculator. Natural log of 4 divided by 2. 0.693. That's pretty good. 0.693. Now I found r. What do you suppose I need to do with this r? Plug it back in. to where, and that we can figure out P. Yeah, so we can figure out.
Change the time, right?
So I can plug that back in. What's really nice is I'm going to go ahead and just use that decimal. So 100 that's not right. 100 divided by e to the 3 times my answer. So remember the A and S button, answer, is a great one to use because it's going to use the entire, it actually goes back and uses the exact answer here, which we can actually simplify. P turns out to be this lovely, perfect 12.5 number. That only happens in math class. All right. We started with 12 and a half bacteria.
I didn't get half.
I know, it's totally stupid. Okay, so what I'm going to do then is now that I have this information, I can do that and write my model because it's really important to have a complete model. So A equals P, which was 12.5, times e to my R value, which is 0.693-ish T. So plugging in my initial quantity and my rate, and then I can answer the question that we actually want to know. So the first thing was figure out the R, solve for R, solve for K, and then write the model, and then answer the question. How many bacteria will there be after 6 hours? What are we supposed to do? Yeah, so T equals 6, so we're going to plug that in. And again, I think I'm going to go ahead and see 12.5 e to the, oh, you know what? I'm just going to go grab that times 6. I don't know if you saw what I did there. Did you see that? Let me do it again. Watch carefully. You see it? Okay, 12.5 e to the, oh, crud, I erased it. Oh, Jesus Christ, that sucks. All right. I'm just going to type in that exact answer right there. Natural log of 4 divided by 2. All right, there we go. Times 6. Okay, never mind. All right. Get about 800. Exactly. 0.693 times 6. It's approximately 800 bacteria.
Scroll back.
Can I scroll back up? Oh, Jesus, I could have. Oh, well. That's okay. You can type it in exactly, too. It works just as well. So about 800 bacteria after 6 hours. That was not the only way to do it, and by God, it wasn't the easiest way to do it. If you're good at messing with time, it becomes much easier.
Sorry.
Yeah. All right, let's try some more. Example 2. Half-life. The half-life for a radioactive isotope is 24,360 years. If the initial quantity is 2.16 grams, how much will remain after 10,000 years? I'll give you guys a second to write that down. Your book has all kinds of crazy formulas for this stuff, but I hate teaching formulas. I'd rather go with what we have, which works just fine. Might take a second or two longer, but it's nothing else you have to memorize. How much will remain after 10,000 years? So the first thing that we want to do is use half-life to solve for K. And we're going to take that K value and be able to write our model then. But before we do that, I want to talk briefly about what half-life means, okay? So half-life, if I were thinking about a graph, we're talking about time versus my quantity, which is why your book uses Q for quantity instead of A for amount, but quantity and amount, whatever. So my quantity of my radioactive substance means it started when time was 0. We started at right here, which I'm going to call 2.16 grams of whatever this radioactive thing is. Okay. We started at 2.16 grams. And what this half-life means is that after 24,360 years go by, we have half of the quantity we started with. So after 24,360 years go by, how much do we have left? 1.08 grams. We have half the previous amount remaining. And then after another 24,360 years go by, which is a whole lot of years, how much do we have left now? 0.54 grams remaining now. And so this amount is decreasing as time goes by. Will we ever have 0? No, we're always taking half, taking half. Are we going to get really, really close to 0? Absolutely, infinitesimally close to 0, okay? But this is important to understand because if you think about it like this, then once again, we have ordered pairs, meaning my initial quantity, the P, was 2.16 grams. So I'm going to go back to my exponential growth or exponential decay model and use that. Nellie, what's your question?
Did you mean to put that slash right there?
Slash.
The slash under the 44 graph?
Oh, I was me drawing a curvish. Exponential decay curve. Okay, so 2.16 was my initial quantity of this radioactive substance. So I can plug that in. And then I also know that after 24,360 years go by, how much do I have left? 1.08, or half of what I started with. That's what half-life means. So I could write half of 2.16 or half of whatever that initial amount is, or I could think about it and use 1.08, okay? How do you solve for K? Or I put K, R, whatever. Divide by 2.16, sure. So what is 1.08 divided by 2.16? Oh, it's 1/2. Look at that. It's half-life. And look what factor we get. A half. The same thing occurs when I ask you, hey, how much time does it take to double your initial investment or triple your initial investment? When you divide, you get that 2 or you get that 3. The same thing is here. After so much time has passed, we get half left over, okay?
It all makes sense.
It all makes sense. It's crazy. Math is totally logical. So now how do we solve for R? Natural log, both sides. So I have the natural log of 1/2 equals, good, 24,360 R times the natural log of E, which is 1. And then what do we have to do to get R by itself? Divide by that crazy 24,360. And we get R equals, let's see what happens here. Natural log of 1/2 divided by 24,360. What is that?
Oh my God.
What does that mean?
Oh, that's the rate of deterioration.
Oh, you just
That means it have to
have to.
24,000. Wait, no.
No, that's the rate of
What does this mean? What does this answer mean?
that's the rate of deterioration every year.
It's scientific notation. This is how your calculators give you scientific notation. So negative 2.845 times 10 to the negative 5 power. That is a very, very small decay rate. All right. Frankly, I'm just gonna. Well, it's still in my calculator, so really, really small. Now I'm going to go ahead, since I have that, and write my model. So my model is A equals my initial quantity, 2.16 times E. I'm just going to leave that exact. Natural log of 1/2 divided by 24/360 times T. So here's my model. I just used the exact answer instead of rounding it off. This is crazy to write. What do we have to do if we want to find out what happens after 10,000 years? So T is 10,000. So here's my question. Before we do that, look at this picture. Are we going to have more than half of what we started or less than what we started? Half of what we started. More than, sorry, that was a bad way to say that. I know that after 24,360 years, I have 1.08 left. Are we going to have more than half or less than half?
More.
More than half. Yeah, because 10,000 is like right here. So we're going to have a little more. Somewhere between 2.16 and 1.08 would be an excellent guesstimate. Okay, 10,000 years is a lot less time. So we're going to go ahead and plug in that 10,000. So if T equals 10,000, I'm going to plug that in there. And I'm just going to go ahead and type it directly into my calculator because that's what they're for. Oh, and I can pull up my answer because I still have that previous decimal in there. So answer times 10,000. Watch your zeros, ladies and gentlemen. 1.625 grams. After 10,000 years. Still a lot left.
Yeah, just do it in your head real quick.
Yeah.
So,
Lovely how beautifully that came out. Math doesn't happen like that. So writing a model is pretty much key. Find R, write the model, then answer the question. A three-part thing pretty much happens all the time. All right, questions so far? All right, last one. We got 7 minutes to get this done. Okay, let's go.
There's 7
7
minutes.
minutes on the
No,
recording.
on my recording.
Better sure talk fast.
Yeah, you won't finish. The fish population in a lake can be modeled by P equals 10,000 over 1 plus 19 e to the kt, where T is measured in months. Time is measured in months. So I have some information. The population after 7 months is 1,759. Wow, that was exact. Do you think they counted every single fish?
Yes.
That's completely ridiculous. So no, that would never be like that in real science. This is the fancy world of math, where everything just works out great. Okay. So first and foremost, they're giving us this model. This is more like what you're going to see in your homework today, where they're actually giving you a partial model. And what do you suppose we're going to do to complete the model? Plug in stuff and solve for what?
K or T?
You got to figure out the K. So we have this model, P equals 10,000 over 1 plus 19 e to the kt. And with any model that you're given, the first thing you need to do is understand what the letters mean. So what does P represent?
Popular.
Yeah, it's our population of fish. So it's our fishy population. My kids banded together and bought themselves fish in a fish tank since our dogs died, so. Sorry, what's time? T.
We gotta go 6 minutes.
I don't remember fish being so entertaining, but man, these fish are like puppies. You come in the
They're funny.
room and they're like, hello, how are you? Like, wagging their little butts.
Their little hands, man. They're so cute.
Okay. What do you suppose we need to plug in then? 7 goes in for time, and 1759 goes in for T. Okay. 1759 equals 10,000 over 1 plus 19 e to the k times 7. Okay. Now, ladies and gentlemen, for all the marbles, how do you solve for k?
Get it over.
Multiply by the denominator, or also known as cross multiply. Ladies and gentlemen, how many of these have we done?
Oh, so much.
A lot.
The whole year.
A lot. All right, so 1759 times the denominator, and I'm just going to leave it because I don't want to distribute that 1759. What can I do instead of distributing? Divide the 1759. Yes, I'm going to do that. Get it out of the way. So I'm left with 1 plus 19 e to the 7k, and in my calculator, I'm going to have a nice running decimal here. 10,000 divided by 1759. And I get 5.685, blah, blah, blah. And now what should we do? Subtract 1. So subtract 1, and I'm going to get 19 e to the 7k equals 4.685, dot, dot, dot. Then what? Divide by 19 in my calculator, and I get e to the 7k equals 0.2465, yada, yada, yada. And then what? Natural log. Ellen is a TV show. In math, we take a natural log. All right. What happens to the natural log of e? It's 1. So we're left with 7k equals the natural log of this. Again, in my calculator, natural log of my answer. So using the answer button, really useful here. I get negative 1.4000. Wow, that's really nice. And then divide by 7, and I get negative 0.2. Gotta love math class. K equals negative 0.2. So nice. That's great. So we found k, and we can complete the model then by plugging it in. Negative 0.2 t. All right. So here is our complete model. Now, part B. What do we need to do to figure out part B? Put 5,000 in for P, and what are we doing? Solve for T, which basically means we get to do the whole process again.
Oh, you're.
Let me just say, you better know how to do this. Okay, so we are solving for time. How do you start, ladies and gentlemen? Cross multiply. Very good. And what are we going to do with that 5,000? We're going to divide by 5,000. So I get 1 plus 19 e to the negative 0.2 t equals 2. Where did the 2 come from? 10,000 divided by 5,000. So we cross multiplied and then divided by the 5,000. 10,000 divided by 5,000 is 2. And now what? Subtract 1. 2 minus 1 is 1. And then what? Divide by 19. So I get 1/19th, and I'll just leave it because that's a fraction and it's fine. And then what? Natural log, and that's fantastic. Natural log of e cancels out, leaving negative 0.2t equals the natural log of 1/19th. And then divide by negative 0.2. So t equals the natural log of 1/19th divided by negative 0.2. And I can type that in. Look at that. Natural log of 1/19th divided by negative 0.2. And I get like 14.7 months. Thank you for the unit there. Months. THS. Because we were talking about time in months. All right. The population will be 5,000 in about not quite 15 months. You guys have any questions for me?
Miss, you finished 6 seconds.
Got 6 seconds left. That's awesome. Okay.
God.